Welcome back, everyone. We have our second philosopher of the workshop so far. Simon is very appropriately also trained as a physicist, and he's currently at the University of Groningen, and he's going to talk about, Simon Friederich, he's going to talk about the observer reference class problem and researcher degrees of freedom in multiverse cosmology.
Now, is it on?
Yeah, it is on.
Okay, thanks. So the structure of my talk is that I will first give a rough characterization of what I mean by multiverse theories in the first place, and why I think, at least in principle, to take the multiverse idea seriously is reasonable. So it's not. I'm not categorically against theories that fall under this label. Then I will critically comment on a particular proposal brought forward by cosmologists Srednicki and Hartle for how to deal with the so-called typicality principle, or principle of mediocrity, that is often invoked to make multiverse theories testable. I will round off my criticism by proposing a somewhat different reaction to the conundrum that Srednicki and Hartle are aiming to address, and then finally, the section that I already alluded to is the one where I will comment on the relation to the replicability crisis. So I will be brief in the beginning about multiverse theory, so you can ask questions later. So what do I mean? I don't have a precise definition of what I regard as a multiverse theory. Basically, I intend this to mean a theory according to which the laws, some aspects of the laws, whatever exactly you mean by the laws, and the constants, maybe background boundary conditions of the universe that are still relevant, they are somehow environmental. Yeah, so they might vary over space-time and not on long scale, so that we can't just very easily probe their variation. So the idea would be somewhere very far away in space or time, gravity is much weaker or stronger or whatever. That would be a multiverse theory. Of course, paradigmatically, you might think of just spatio-temporally completely distinct universes, or just where you causally isolated universes, as in the maybe the most famous multiverse proposal, which is the landscape multiverse that arises from the combination of eternal inflation and string theory. So why consider those in this generality in the first place? I see roughly three motivations. First, it's just a possibility. Yeah, so it's just a possibility that what we can probe is just not everything, right? So it could be that just our causal range, that the range of our experiments is just only sufficient to probe a small amount of what there is. It could be the case that the laws and constants are just very different elsewhere. Yeah, that would be the first motivation. Then we have this, so string theory is at least one of the serious candidates for combining our best theories of fundamental physics, and inflation is also a serious paradigm for early universe cosmology. Taken together, they are it's at least suggested that they yield a particular version of the multiverse idea, where you have these pocket or island universes that pop up in an inflationary background, where you don't have causal contact between the different regions, which effectively realize different higher level theories, where the standard model, for instance, counts as a higher level theory. And then finally, maybe most important, most interesting, most intriguing from the philosophical point of view, multiverse theories have been suggested as a response to the claim finding that various aspects of the laws and constants seem fine-tuned for life. So here are some claimed examples of constants that seem to be just such that there can be those complex structures that are needed for life. I won't go through them all, because the focus of this talk is not on fine-tuning. And the idea here is, of course, that the idea that is most prevalent in the literature here is that if there is a sufficiently varied multiverse, then it's not surprising, if the multiverse is big enough, there are some sub-universes of the multiverse where the conditions are right for life, and then, of course, this only there is where we can find ourselves. So by inference to the best explanation somehow, because this is an elegant explanation of why there is life, why we would find ourselves in a life-friendly universe despite the required fine-tuning. There is likely a multiverse, but the problem with this suggestion is that it is somewhat unclear whether the existence of multiple other universes besides this one would actually make it somehow more likely, less mysterious, that our universe, this one here, is life-friendly, right? So if you find something remarkable where you are, and postulate various other places where less remarkable things happen, have you thereby made it less remarkable what happens where you are? So there is a big discussion about this in the philosophy literature. I think that physicists haven't sufficiently looked into. Actually, it's called the inverse gambler's fallacy charge. I will not look into it today also, but it's very interesting, and I think it's as far as I see it, the debate is deadlocked, right? So you can see it. You can look at the matter from two different perspectives, and both are coherent, and I can't find a way to break the impasse. Whatever. So I try to devise a better fine-tuning argument for a multiverse, outlined here, will hopefully be published soon. Well, I think other people will criticize that one as well. I think it is better because it's not susceptible to the inverse gambler's fallacy charge, but it accomplishes less if successful. I think all in all, those fine-tuning considerations make a serious case for earnestly looking at multiverse theory. So it's not just arbitrary the pull to take them seriously. So, but of course, just saying in general terms, well, there might be a multiverse. That's not physics, right? That's not really worthy. That's not very interesting. yeah, for if we want to find out about the world. So we want to be able to test concrete multiverse proposals, and that's very difficult. Yeah, as for instance highlighted by George Ellis and Peter Voigt and others. So there are some trivial exceptions. So for instance, if you have a multiverse theory where the multiverse, where you don't have a sub-universe that has anything like standard model physics, okay, that's ruled out, that's testable. Or you could have, that's more interesting, you could have a multiverse theory, many constant parameters don't scan, right? They are uniform over the entire multiverse, and they are really the ones that we find. And this is a non-trivial prediction that you don't get from other theories. Okay, that's also confirmed in a way. It's a bit of a hypothetical case, but so if a multiverse theory behaves unlike a multiverse theory in various respects, then it's perhaps testable, right? But what if it behaves like a multiverse theory? Okay, so what is recommended in the literature, and I think indeed reasonably so, is that we use a so-called anthropic approach, which tries to extract predictions or post-dictions from multiverse theory by asking, well, if the theory is true, what would a typical observer find, right? And if the typical observer would find what we find, then that's good for the theory. Yes, Astrid.
A bit more specific, what do you mean by typical? I mean, where do you take the map?
That's basically my talk. Yeah, okay. Yeah. I think it's a super reasonable, obvious question. Yeah, that's just the hint. Yeah, the hunch. Yes.
So you mentioned inflation at the beginning.
Yeah.
As one possible scenario, but there you can have bubbles forming in the universe.
Yes.
So in some sense they are in causal contact, and you could search things like collisions of bubbles in the past.
Yeah.
Is that
That's
not a multiverse?
actually, whatever. Is it a multiverse? I think nothing much hinges on the terminology. Yeah. So in a way, if you can, in the text underlying this, I mentioned this also. If you find very clear imprints of bubble collisions that are really exactly as that observations conform precisely to what you would expect from the scenario, then of course, then it's also testable, whether it's still a multiverse theory or not. Yeah. Okay. So that seems testable. Yeah. Right. So, but but I don't think that raises special philosophical challenges. That is probably just very difficult to really make those. To say, yeah, if there are bubble collisions, we will find such and such patterns, and then say, okay, this is what we find.
Unless I made a mistake and I misunderstood what you said, I believe you said at some point that this multiverse idea, the values of the various constants would be the same, or they could be the same.
In overall universes?
Yes, but I believe that's something that by definition does not exist in the multiverse, because that's the idea. So
you're right. Yeah. No. It could just be the case that among many parameters, a few are uniform.
This can't be, because then I think that this goes against the idea of the multiverse.
Yeah,
it shouldn't be the same among these people. I don't believe in the multiverse, but other people who come with that is the idea that you have this possible universe, and we leave the one that light, that's completely anthropic principle. I don't adopt this approach, but I cannot. That means that the values of these constants are by default not the same.
That they all scan. Yeah. Well, I just mentioned this for the sake of completeness, and Brian Greene mentions it in his book on multiverse theories as a first easy case where testability looks better. But whatever. Yeah. It's what I said. If a multiverse theory just doesn't behave like a multiverse theory, then it's probably testable. Okay. So famous examples of attempts to make this work in practice are to the anthropic reasoning in general are Weinberg's argument that the value of lambda that observers can see is constrained to up to a few orders of magnitude higher than the measured value, which is much smaller than what we would expect from applying naturalness. And then there are more recent arguments by, for instance, Vilenkin and then Busso and co-workers. Their results, well, how they come to the results is a matter for the rest of the talk, but the results seem to say that typical observers will find values of the cosmological constant that are in the landscape multiverse are really in the order of magnitude of what we find. So they basically say they here with concrete numbers, they say that for the probability density, the distribution over, they say this is a confidence interval, but it's somehow misleading. For the probability density for what observers will find, so that's actually a frequency distribution over the landscape multiverse. It's such that the measured value falls in the between -1 and +1 standard deviation of the mean, and so that could be regarded as a huge predictive triumph of the landscape multiverse. But I don't think we should be so quick. So what about typicality? What about the reference class of observers with respect to which we should assume it? Is it reasonable to assume it at all? So it has different names which highlight some more different aspects of it, but here are, I think basically, I take these to be basically the same. Vilenkin's principle of mediocrity, Bostrom's self-sampling assumption, Elgar's indifference, which is a bit more restricted. I like Bostrom's best, which is you should reason as if you were randomly sampled from a reference class of observers, right? So you need a reference class of observers, and then reason as if you were a random sample from it. So how could one motivate this idea? So Bostrom has this dungeon thought experiment. Let's assume that the world consists of a dungeon with 100 cells. Each cell there's one prisoner. 90 of the cells are painted blue on the outside. The other 10 are painted red. Each prisoner is asked to guess whether he is in a blue or a red cell. Everybody knows all this is set up. And you find yourself in one of the cells. What color should you think it is? The answer is blue with 90% probability because 90% of the cells are blue. If you use probabilities for this in the first place, then it's the terminology that has been used for this, has been introduced for these probabilities, is that they can be derived from a so-called zero-graphic distribution. That's what Srednicki and Hartle call it. They use the letter xi for it. For each, the probability that you should assign to being any observer in a specific cell with a cell number i should be 1 over n, where n is the total number of cells. So that's Bostrom doesn't have a very strong argument for this, for why this should be your answer. But I think the appeal is somehow clear. Well, let me just. He has sort of an argument, namely that if you say, if you let the prisoners make a collective bet, and they all have the same information, they must all make the same bet, then this is the only bet, according to these probabilities, that will avoid a sure collective loss for them. Right? So that's you could also construe this as a special instance entropy maximization, information entropy. Whatever. So
I don't understand this point about the bet. You said that if 90% of them will find themselves in the blue cells. And they bet they're in the blue cells?
They bet that with 90% they are in the blue cell. Yeah. Otherwise, if they bet differently, if they all must make the same bet, then they will lose. Yeah. So, but of course, the question is, in as much as this is reasonable, you can already attack the Bostrom motivation, right? But I will grant. Let's grant the the multiverse enthusiasts that, because that's what they crucially rely on. But of course, there is a hugely important question about what should be a reference class of observers. In the prison example, we said there are 100 observers, okay, and they are our reference class. But what should be the reference class in cosmology, where we have people and extraterrestrials and ants and rocks and whatever? I mean, supercomputers. So there is another thought experiment that highlights this. Suppose, which is due to Hartle and Srednicki, an older paper by them. Suppose we have a theory T1 predicting that there is no life on Jupiter, and theory T2 that says that Jupiter is populated by intelligent beings and has population size J, much greater than the human population H on Earth. So there are many Jovians. Jovians are the observers on Jupiter. According to T1, we are typical observers in the solar system, because the human beings are the only ones worth taking seriously. And according to T2, we are not, because the Jovians vastly outnumber us. Hartle and Srednicki argued that it would be absurd to dismiss T2 merely because it makes us atypical. Right? So that it seems a bit odd to say the Jupiter theory must be wrong because it would make us atypical. So at least if J is large enough. So a lot of course, this was somehow clear from the beginning, a lot hinges on the observer reference class. This is just meant to highlight that. But it's not really about Jovians. How to deal with that?
And also,
yes?
I mean, a huge thing already with the first example is it works if it's a number of
right.
cells. I mean, that's the real issue as well, isn't it?
It's another issue. I will come to that, because that's also, that will also turn out difficult to make true. Okay, so to solve the problem of justifying typicality and the use of a specific reference class, Srednicki and Hartle in their newer work propose that we should test frameworks of theories and zerographic distributions. So they say cosmology basically has entered a new stage. We should not only just, as we did previously, test theories T, we should also test zerographic distributions. We are physicists. If things are brought up, we test them. So this holds also for zerographic distributions. This is their formula for how they suggest to test the probabilities that we should assign to zerographic distributions and theories, given our background knowledge, DO, should be computed according to that formula. And they think that these probabilities factorize the probability distribution that assigned to that we should assign to the theories and to zerographic distribution should factorize. We should really treat them totally analogously. So I think that's a very weird assumption from the start. There is much that is weird about it, but because for instance, basically assumes that the observers are the same across all theories, right? Because only then can those decouple, which is probably not possible because different theories probably entail the existence of different observers. Whatever. I mean.
Sorry, I get completely confused.
Yeah.
Because from what you said before,
yes.
The observer, which means the reference, is going to influence the result you will get.
Yes.
So it's impossible to test the observer reference because you are the observer reference.
The observer reference class. Yeah, I will come to the conclusion that this is not something that we can test.
So to me it's obvious from what you said before. So this makes no whoever said it. I don't think.
So James Hartle is
I don't mind, but the point is that
he's not obscure, I think.
Yeah, but it's not that somebody said it. I have to believe it. So what I'm saying is that the observer, from what we just saw and we just correctly said, is going to influence the result. So we cannot test the observer reference. It's going to influence.
Yes, I agree. We cannot test it.
Even if whoever said it's part of your name, it makes to me.
I agree. Yeah. I agree that the observer reference class is not something that we can test. Basically, the observer reference class sits in the zerographic distribution because it's those arguments that are assigned a non-zero value. Yeah, and if the distribution is uniform over those, then it's an indifference distribution. But basically, yeah. So if they were right that we could test xi, then we could somehow test which is the correct observer reference class. But I'm saying no, xi is not testable. It's not the kind of thing that you can test. Why not? So here is a way, an attempt to say why not. So if we define a probability distribution over zero-graphic distributions, then that's a second-order probability distribution, which is in principle fine. You can, they are not by themselves incoherent second-order probability distributions. For example, in model selection, you have a model as defined by a probability distribution over probability distributions. But still, I think there is a huge difference here because there is just no correct reference class, contrary to presumably theories where there is a correct one. So just to see this, to see matters, imagine that you have a theory according to which there are half of the universes are red and the other half are blue, all are populated by observers or so, and you find that our universe is blue, and then zero-graphic distribution that assigns non-zero to you being in a red universe will be punished for that, but not ruled out. So you would, after finding yourself in a blue universe, you would still, if you initially assigned a non-zero value to that probability distribution, that would stay non-zero after having taken into account that information, and that to me makes no sense. So if you find you are in a blue universe, you shouldn't assign a non-zero value to a zero-graphic distribution that says with probability that you are in a red universe. So this is, I think, what they have overlooked. Otherwise, I cannot. So what we can, of course, do is perform if we accept this concept of a zero-graphic distribution, we can take various ingredient zero-graphic distributions and weigh them, right, by give them weights, and then say this is really our ultimate zero-graphic distribution. That's totally coherent. And then update the weighted distribution. Right. So basically we are back to the start. I think I have engaged with Srednicki and Hartle because their paper is in a way very clearly written, and they have taken this issue seriously, but I don't think it works what they propose. So the question of if we think typicality-based reasoning, indifference-based reasoning is worth a try, which reference class should we use? Is open again. Yeah? So because testing a zero-graphic distribution is not a thing. So, but I think there is a straightforward criterion that makes a lot of sense, which I call the background information constraint. So if we say we have somehow fixed what our background information DO is, so the information that we take as a given when we try to predict or, as it were, post-dict the value of some parameter. So let's assume we have that as a given, then including the observer reference class, precisely those observers who you could possibly be in view of DO being your background knowledge. Right? That makes a lot of sense. So go back to the prison example. If you know you are a prisoner, but you have no idea in which cell you are, then maybe the reference class of prisoners is a good one, right? But if you don't even know that you are a prisoner and there are people outside, then this is not a good reference class for you. So the good reference class to use will not be somehow an effect of the world, but just reflect which aspects of your background knowledge, how they narrow down who you could be, right? And perhaps perhaps that information DO is not neutral between the observers that you could be. Perhaps you have a hint, for instance, in the prison example, that you are in one of the earlier cells, and those tend to be red or so. Then indifference is probably not a good assumption. Yeah, of course. I think everyone would agree with that. So. So assuming that the information is indeed neutral, I think that's the only way how you can justify this using an indifference principle of self-locating belief. you should include in the observer reference class those observers who you could be in view of DO. So this is reasonable only if typicality is reasonable only if DO is neutral between which of the xi in that reference class you could be. So it's important to realize that this DO need not be our actual knowledge. So, for instance, I think we can concede to the people who want to derive a prediction for the cosmological constant from the landscape multiverse that this is somehow possible. They must say what they take as background, which other constants they take to have measured, and then say for observers who have those measurements as their background knowledge, what would they predict for the cosmological constant, and then see what they get. So, does this solve the problems? In theory, I think it goes some way towards solving them, but in practice not. So that's why I ultimately come down on, I think, George's side. But in principle, yeah. So let's see this with respect to the humans and Jovians, the Jupiter beings scenario. So there is just no uniform fact, no universal fact of whether the Jovians should be included in our reference class or not. If we assess whether T1 or T2 is correct, is done on background knowledge, based on background knowledge that gives away the fact that we are humans, then we should only include humans in our, or even just ourselves, so just the one person who we happen to be in our reference class, in which case we don't need this apparatus. If we use rather impoverished background knowledge that is compatible with us being somehow intelligent beings on Jupiter, whatever exactly that means for the however exactly that would manifest itself in the background knowledge, then we should use the Jovians in our reference class and punish T1 because it makes the finding that we are humans somewhat surprising. Yeah. Well, in theory, so the issue is solved, but for implementing it in practice, so that's what I think would be the correct way of using the nomenclature of Srednicki and Hartle to spell this out. But in practice, I think my investigations make clear just how tall the order really is that the multiverse proponents would have to live up to make the theories testable, because they would have to show that it can be determined unambiguously which and how many observers you could possibly be given your chosen background information DO for all theories T that you wish to test. So basically you must have figured out all the atomic physics and chemistry and whatever for those other universes with different higher level physics, variations from the standard model or whatever, and be able to count them, basically say, at least have a very good idea of the order of magnitude to really do this. Yeah. And then of course you should also, for this background knowledge DO that you use in each specific case, be able to motivate a good prior probability for the theories. So you must say, if I abstract, for instance, from what I know about the value of the cosmological constant or whatever, I keep other things. Given that background knowledge, how reasonable is it to believe that the theory T is correct?
So this makes no difference which type of multiverse you're talking about? Like the quantum version?
Oh, the Everett, I'm not talking about Everett. I think Everett is problematic on other grounds. I am really interested in theories that entail some variation of fundamental parameters. So, of course, there could be you can have versions of Everett where you have superpositions, so different branches where different values of the constants are realized or so. Then this becomes intertwined. But I can't say anything clear about that. But in principle, the different multiverse theories, are taken into account by saying we have this variable T here. So, but the first desideratum is especially, the second is a general issue, yeah, the problem of priors if you use a Bayesian approach to theory testing. But the first is I think, if taken seriously, is actually insurmountable. So, what is done in practice?
10 minutes left.
Yeah, which is, and I will need 12. Okay, let's see. So we started out with a successful claim prediction of lambda in the Busso, Harnick, Cripps, Paris paper on where they made this, yeah, set in a landscape multiverse. So the value of the cosmological constant that we find here is really among the most typical ones that you can get. So how was it done? To connect their discussion with mine, which is, I think, possible. It's the notion of a zerographic distribution indeed helps again. So now we must give it an index for the theory T, because different theories T lead to different observers. They entail different observers, so that must get an index. And then this is the probability, if T is correct, of finding yourself in a region with a value lambda, so where lambda has a specific value lambda, given your background, assumed background knowledge do. That's assumed to be proportional to the number of, well, a number of subregions that, so M ranges over subuniverses or regions of the multiverse, where lambda has that value, times the average number of observers who see that value given your in one of those regions, right? So in this is the number of regions where lambda has that value, and that's the average number of observers in universes with that where lambda has that value. Okay, but the problem is, as Julian has already pointed out, for the landscape multiverse as usually set up, I think George is critical of that as well. That there are infinities popping up all over the place, namely the regions where constant has a specific value are assumed to be infinite in number and infinitely large, which means that you need to regularize the thing somehow. You must find you must first focus on a finite region and then define a limiting procedure and look at it, what happens in the limit of taking the size to infinity. This is, I think, this is how I understand the so-called measure problem. And the problem is that there are various different mutually incompatible prescriptions for taking the limit, for doing this regularization procedure, and it's somewhat surprising to me. It turns indeed out that cosmologists think that we will find the right measure by ruling out the wrong ones, which are those which don't lead to the right empirical results. Good to see you laugh. That already makes the predictive success somewhat less impressive, I would say. So, for instance, and I think it's there's a paper by Tegmark from 2005 where he really explicitly says we must find out which measure, which regularization procedure nature subscribes to. He uses those words. And I think he no longer talks that way, but this is still, or I don't know really how the papers are a bit less dense on this now than they were 8 years ago or so. I think people have maybe largely abandoned this approach, but still, I'm happy to take it up, right? So I think it's plausible that there is not a fact about which measure is correct, right? So how would that somehow how should that physically happen that there is a correct measure? So there could be ultimately how their criterion is just predictive success, but that it's well, that's just it's not clear how this would somehow relate to the physics, right? So how could, for instance, you can ask yourself, if you have two possible, could there be the same multiverse twice, which subscribe to different measures, in which nature subscribes to different measures? Well, do measures supervene on other facts? So if they supervene on other facts, then I think we should study those other facts, right? They are probably to do with what observers are there, okay, but we shouldn't shift this to the question about the correct measures. And if measures do not supervene on multiverses, then it's difficult to see what the point is, right? So they are empirically inaccessible then. Okay. Another big problem is, that we would have, in principle, as I already said, have to figure out all the chemistry and whatever in different universes. It's difficult enough for our own, and to be able to see how many observers who we could possibly be are there in other universes. A common strategy to get a handle on this is to use so-called observer proxies. For instance, the amount of matter clustered in giant galaxies per baryon. This is motivated from the cosmological constant, right? It's thought that in the larger values of the cosmological constant, which are still compatible with galaxy formation, they don't lead to as many galaxies as we have here. So observers are less prevalent in those universes. So that's how this proxy is motivated. But if you look at it just really as written here on paper in the abstract, it's not clear how why basically the efficiency of converting baryons to galaxies would be a reliable proxy for observers who we could possibly be given our background knowledge. And then another one that has been proposed comes with a specific measure is entropy production in the causal diamond. Of course, entropy production is something the advantage is that it's very general. So it's not. So, for instance, there could be other universes where baryons are not even defined because the effective physics is so different, and entropy might be defined. But I mean that's an extremely coarse criterion. So the problem is that it's not a controlled approach. So what's going on here? Now the promised comparison with social science. What is going wrong there when studies don't replicate and bogus findings are published where people find a decade later that they cannot replicate the effect? I think one of the main causes identified by these brilliant statisticians, Simonson, is here nicely brought out in this passage. They write, the culprit is a construct we refer to as researcher degrees of freedom. In the course of collecting and analyzing data, researchers have many decisions to make. Should more data be collected? Should some observations be included or excluded, like outliers that seem weird? Which conditions should be combined and which ones compared? So which variables should we control for? Like if we study, for instance, the gender pay gap or so, what should we control for, what not? It is common and accepted practice for researchers to explore various analytic alternatives, see what happens if we discard this or that as an outlier, to search for a combination that yields statistical significance, and to then report only what worked. So you check whether perhaps the hypothesis that you have holds for various subgroups of your sample, or if it works if you exclude certain somewhat weird outliers where you can find a reason. And their point is that if you do this, your chances of getting your desired result with statistical significance are very high. They are not just 5%, they are more in the ballpark of 50%. It's not guaranteed either, but if you don't manage to get your desired hypothesis confirmation with statistical significance, you may just not publish. So I think that's not very contentious that they have identified here a crucial issue. And now my final lesson that I think applies from their deep insight for the social sciences, that very likely something similar happens here in multiverse cosmology, because what is actually done in those predictions of the cosmological constant from landscape multiverse is that observer proxy and cosmological are used as researcher degrees of freedom, right? That's basically honestly admitted if you say that you test them, that you choose them according to what works. And actually you have more, there are even more researcher degrees of freedom brought out in other papers, like whether you allow for inhomogeneities in your otherwise flat space-time or so. There is a paper on that. And then of course you can also another researcher degrees of freedom is which constants you leave fixed and which you vary, once you try to predict. In theory, if you use my background information constraint, then you should adjust the prior accordingly. So it's not, on a theoretical level, that's not a problem, but that's never done explicitly. No one explicitly adjusts their priors to reflect which parameters they try to account for and which they regard as background evidence. So there is plenty of researcher degrees of freedom. Unfortunately, therefore, those predictions, nice though they look, are not trustworthy. And I don't see prospects for changing this. Unfortunately, I started out in this project also telling basically NWO, I will try to help make multiverse theories better testable, but this has left me somewhat disillusioned. I don't think that these are problems that we can have a good recipe to overcome. It's just so the best chance that we have is still might be what you said is not really in line with the multiverse spirit in the first place. That we have just a multiverse that doesn't behave like a multiverse in some respects, yeah. So finally, one important aspect of the Simmons, Nelson, and Simonson work is that these things that go wrong in the social sciences, that's not because researchers want to cheat, right? They have the best of intentions. It's well known that there is confirmation bias. They honestly believe that they make the right steps, but they are driven by the desire to see certain things as confirmed. And I think the danger that this will happen in cosmology is just too large. Yeah. Thanks.
We're plenty of time questions to start with students. Come on, guys. No? Keep your hand up. James first. Your hand up if you've got a question, and I'll put you on the list.
Thanks very much. Can you put up the slide where you had that factorizability assumption? I mean, I know we're just sort of, maybe we're sort of attacking the corpse here after your critique. But that struck me as particularly crazy because it seems to say factorization is normally, the definition of independent events, right? That the probability factorizes. So what that would be saying is that the probability of there being observers like us would have to be independent of what theory was true.
Yeah, I don't understand.
But that's completely crazy because on some theories it would be impossible for them to be observers like us. So we know that the probabilities are.
Yeah. Yeah, I really don't understand why they wrote this. Yeah. And then they say the good thing about our formalism is that we can test the zerographic distribution by competing different zerographic distributions against each other for the same theory. So which is.
So I hope you're right that we've reached peak multiverse, and I just sort of finished by posing the following question for everyone else to think about. I was a few years ago, I was thinking of writing a paper called A Multiverse as a Sign of a Degenerating Research Program.
Right.
And I just wonder if anyone can think of any, because you get it in set theory, you get it's sort of set theoretic reductionism, where people can't decide what set theoretic axioms are true. So then they say, it's a multiverse, that solves the problem. And you get it with David Lewis's sort of extension of logic, and you get it with string theory landscape, and you get it with Everett. I don't find any of those.
Right.
good research programs. So I wonder if anyone's got any counterexamples to our hypothesis.
Well, let me just repeat that. I think there are very good reasons to take the multiverse idea in general very seriously, at least in this sense that the parameters might vary across or whatever. It's just that I very much hope that it's not true, because it would be so difficult to find out. And in other contexts, yeah. So that's of course what you have mentioned are very, very different ideas. To use the multiverse label for them all is
right. But in every case, you seem to solve the problem by fiat, right? Because
yeah. Right.
Thank you for a really nice talk. I've got three brief comments. The first is that there's an issue you kind of touched on, that people looking at the multiverse, they look at stuff like, do galaxies form, do stars form, not whether life will form. Dave and I have got a really nice project looking at, if you vary the fine structure constant, will complex molecules like DNA be able to form, which is actually a really nice extension of the circuit. The second comment is that the word infinity is used liberally throughout the multiverse literature, and I think this is a major problem. I've just been completing a paper with two colleagues saying that infinity, as David Hilbert says, never occurs in physical reality. And the final comment is, does the multiverse actually solve the anthropic problem? And from my viewpoint, all it does is shift it up one, because I can easily construct a multiverse in which none of the universes in the multiverse allow life to exist. All you do is you put in a higher level of assumptions about physics and constants and so on, and all of the basic questions reoccur at the higher level. For instance, I could make you a multiverse in which there's a universe which doesn't allow life, and the multiverse, the universe creation mechanism in the multiverse punches out millions and millions of copies of this one universe which doesn't allow life to exist. So you haven't actually solved the anthropic problem at all. You've just displaced it one level higher, in my opinion.
So I think I fully agree with your first two remarks, but about the third, I'm not sure whether I understand. So
Weinberg's assumption is that the cosmological constant probability is flat. If you look at the paper there, I could easily produce you a mechanism where the cosmological constant prediction is peaked at 10,000 times the current value.
Yeah, the argument for the flat distribution there is that that from as far as we understand string theory, the point lambda equal to 0 is not special. So because on the if we look at the Planck scale, then the intervals we are looking at are tiny, so it's approximately constant there.
Okay, but I could in principle tweak string theory.
Of course, yeah, of course.
Any more questions? I was going to ask something I've always slightly been confused by. Is how do we, I think that using complex molecules as a proxy for life sounds much more sensible, right? But how do we even know that that's, we don't really understand life. How do we know that life can't form out of pretty much anything? How are we ever going to get, constraints on life formation?
Yeah, it's a necessary but not sufficient condition.
It's a necessary.
I don't think why do we know it's necessary? Why do we know it's necessary?
Motivations around what we currently know. I mean,
sure. Why do we know that's the correct way of doing things? How do we know that?
But how do we know they could be quite different physical structures? Conditions that they ain't alright, why not? You could get life in fluids or plasmas or something if there was enough complexity.
Yeah, I mean what people like Brian Greene, for instance, say is that these proxies are preliminary and will be improved as we progress.
But we'll only ever know how our life or lives to be found in our universe were created. So I don't really see what the ultimate.
Yeah, maybe there is some progress on that, but yeah.
No, I think that the answer that you had, it's influenced by how you phrase the question. I mean, I believe that the answer is defined by the way that you ask what do you mean by life? What do you mean?
Right.
How do you phrase the? So that's why I keep saying from yesterday is a kind of semantics First of all, we should define what we mean, and then we can discuss.
Yeah.
Otherwise, we talk for different things, and we might all agree or disagree.
But I mean, at least in theory, that should not be a problem, because if we use a background information constraint, then I mean, we should take into account all structures who we could possibly be given that background information, whether they are living organisms or they are special living organisms or so. That should be narrowed down by the background information. However, the background information is really able to do that. That's maybe, I haven't really looked into this, but that's at least the idea. So the ambiguity of the definition of life should in theory not be a problem.
Could you just say a little bit more what you mean by background information?
Yeah.
Where does that come from even? I mean,
where does it come from? Well,
I mean, I have quite a bit of background information about my existence and what I've learned in my life, but does that count as background information?
Yes. Yes.
I mean,
so typically in prediction, when we predict new facts, then we can just use the information that we have. That's everything, basically all that is available to us. But things get a bit more tricky if we try to account for things that we have already measured. Then we must say, okay, let's assume that we did not know the value of the cosmological constant, but let's say we knew this, and that. We must be relatively clear on what we regard as the fixtures then, and what we regard as what we try to account for.
Already available information, perhaps. I mean, because there wasn't a known, when Weinberg made his famous prediction, there wasn't a known value for the cosmological constant, but there was quite a lot of other information which was known.
Yes. But my point is a bit that whether that's actual background information or hypothetical, that doesn't, in theory, shouldn't matter.
Last question today.
Yeah, just because I've kicked a little bit of a hornet's nest and upset people by saying that. I mean, just to clarify a little bit, there will be areas within your parameter space, within a multiverse, where you can't even form any complex structure at all, right? So if you crank the cosmological constant up far enough, everything blows apart before you can even form a molecule, before, there'll be sort of parts of this multiverse where there will be just one particle, one electron per de Sitter volume or something like this.
How do we know that you couldn't get organisms?
Because they couldn't be causally in contact with one another. So, I mean, you can't form complex
But that's
structure.
sort of dependent on our theories of causation, our theories, I take your point.
Well, I mean, if you're going to break GR as well, I mean, if you're going to break all of the rules, sure. I mean, but, it's not sort of tech-lock games here.
I mean, no, that was the last comment, but I feel like I'm stretching it, but I mean, quantum mechanics also limits the properties of atoms and what kind of atoms. At least we don't know what possible life is, but we know, according to the laws of physics, how complex structures are, under which conditions complex structures are more likely to form. So I think you have some conditionals there.
I think we've reached some kind of conclusion.